So let's talk about the phenomenon happening in NMR spectroscopy where we get a doublet of doublets. It means you have a doublet and another doublet, and this again you have another doublet. Means doublet of doublets of doublets. So you're gonna get 8 lines, 8 peaks in an NMR spectroscopy. But how are we gonna get this 8 peaks? You see, it's a it's a phenomenon arising if you have a magnetically non-equivalent proton uh, of 3 different non-equivalent proton with the proton in concern. It means our target proton is surrounded by 3 non-equivalent protons, and all these non-equivalents are as single protons. It means therefore a single proton can make it a doublet, and this is going to make this doublet into another doublet, and this thing make these 2 doublets into another 2 doublets. That's why we got into a doublet of doublets. Okay, let's see. First I tell you how I got this, then I will explain you why it's happening like this. So these A and B, this both going to give this kind of doublet of doublets. These 2 protons are diastereotopic, but let me ask you a question: why it's not an anisotropic? Because if there is no chiral carbon here, these 2 protons is going to be anisotropic, but because of this existence of chiral carbon here, these 2 are diastereotopic. And that's how, look, there's an A here. We have a germinal there's a J2 coupling, J3 coupling, and J4 coupling. Look, NMR arises because of magnetic spin, because of the spin of the nucleus, and we're going to apply the magnetic field, and it's going to process. It can be up or down. The spin of the nucleus can be up or down of the nuclei containing odd nucleons. So it can be up or down. So I have an up spin, and I'm going to apply a magnetic field, and therefore it presses its axis. And if I give one radio frequency equivalent to this pressure spin, it's going to change its spin. That's what I put radio frequency here, therefore it will not be confusing. So it's going to process its spin. That's how the NMR works. It's going to change the spin of the nucleus, and a nucleus is not in a free environment. It always have other nucleus near it, and that's going to decide the future of how the NMR spectrum is going to turn out. So I have this A, this HA proton, and I have an HB. It's going to affect its spin, whether based on maybe its up spin, based on whether it's up or down. It's going to give 2 levels to this, and for these 2 levels, at first it's going to combine which is near. This effect is more, and later we have a proton here. Oh, wait a minute, I made some mistake here. It's HC. Okay, this is HC proton. So these 2 levels is going to affect by this nucleus, and again and make it a 4 level, and this proton HD is going to affect this, and it's going to make this a 4 level into an 8 level system. Look, what I'm trying to say is this whatever nucleus in concern having a particular up or down spin, and based on the up or down spin of the another nucleus, we are going to have 2 different levels, and this 2 different levels is this 2 pair. This 2 pair is again going to affected by another nucleus, and like that we got this. Okay. So first I tell why it have a. So I think you got some idea about why it happened like this. If you already have little bit idea about NMR, This phenomenon is easy to understand, I guess. I just want to tell why giving this unique doublets. It's because they have three non-equivalent protons here. So similarly, B is going to give doublets because it have three non-equivalent protons near it. That HA, HC, and HD. And HA is a coupling. It's called the geminal coupling and the vicinal coupling, and it's long-range coupling. Generally, the coupling, this is going to have a higher effect on B than this HC. For usually this split is going to be large in the NMR spectrum. It's going to be 13 Hertz, and the split due to B is going to have a larger effect than this, and HD is having a much lesser effect than this, and HC have an even lesser effect. So what we thought is we are going to get 8 lines, but we only get 7 lines because these 2 lines is going to have an overlap. We only get 7 lines here, and the same thing is going to happen for the HP. The same kind of splitting. We have a 3 non-equivalent protons there too, and that's how it's going to happen. Since I work on the mass spectrometry, like NMR is going to in analysis perspective, NMR will beat mass spectrometry any day because it can differentiate diastereomers, but I have a doubt whether it's going to differentiate enantiomers or like that. We get more information about the of an unknown molecule in NMR better, but in terms of realistic picture, how many of them own an NMR? It's a very costly machine. You need liquid helium and superconducting magnets. On that case, mass spectrometry is have an upper hand. You can library match the spectrum. A lot of things you can do in a mass spectrum. It's very easy. If you already have an idea about the common mass is it's have an edge over in NMR in terms of application perspective. It's widely used. NMR is, how many of you seen an NMR? It's very rare to see an NMR, but the mass I seen many people I seen in many places. NMR also I seen, but I didn't went into that room. But mass is relatively easy to acquire and easy to use. There's nothing much you want to do. Okay, let's come to this thing here, or let's come to this thing here. That is HC proton. It's going to have a very, very complex spectrum because look, this H is going to couple with this 3H and this H and this A and this B, and it's going to have a very, very complex and very difficult to draw this kind of tree diagram for this proton here, but it's going to be a multiplet there. That's how this compound is going to give a spectrum in NMR. We have 2 doublets because of this, and then another complex spectrum because of T and C. These two CH3 are similar. They are magnetically as well as chemically equivalent. These two are chemically equal. Oh, not even chemically equivalent. They're going to give a diastereomers and magnetically inequivalent too. These two are going to give a same spectrum, and HC and HD going to give different spectrum, a good complex one. And this thing is, I think, only going to give it's have a long range coupling, not a okay. It have a long range coupling there. We have 2 things over there. So let's see the spectrum. It was given in this book. This is the book. You see the CH3 C1 is giving a doublet. Okay, there's only one coupling going on there. You see this also giving a doublet because only one D is giving, and we have two doublet of doublets, and HD and HC are giving multiplet complex spectrum, and OH is giving a singlet. So that's the spectrum of this compound.